In this instructional video, I will demonstrate how to use the Train Problem Classifier module of Magellan's Compass software. As described in the first video in this series, Compass runs on a server that I access through Chrome. In the prior video in this series, I showed how to use the Parse All Examples module. After finishing there, we are now working with all of the data in all of the files for this project. There are several user-defined parameters to configure in the classifier training tool. One is to determine class or value from several different options. One generally uses the same method as the one selected in the prior data point selection module. Next is to set the number of data points to be considered in machine learning training. Data points with the highest decision value scores are selected for each binary decision. Seeing what decision value scores exceed random noise in the data is an important point here, and I recommend earlier videos on the random output check module for more information. Finally, the user sets the proportion of the files to be withheld from training and used to test the resulting classifier, as well as how many times this exercise will be repeated with different data selections. The number of examples used for training is important here. There must be sufficient data for training. There must also be enough examples withheld and enough iterations performed that every example is tested by a trained algorithm in one or more iterations. If you need any help in your own analysis along the way, just hover over or click on the help bubbles as we have described in other videos. I am demonstrating the tool using data from a single pair of breast cancer cell lines. The files under study here contain the spectra from proteomic specimens derived from the NCI 60 cancer cell lines, with 12 or more experimental replicates performed on each cell line. This is published data and made available for download at the PRIDE Proteomics Data Repository. Importantly, Compass works for comparative expression analysis of mass spec datasets in proteomics, metabolomics, lipidomics, and many other applications. The output of this tool is a colorized bar that positions individual examples by how accurately the algorithm can predict their classification and by the confidence of this classification. In this case, every classification is correct, so the dark vertical hash mark is all the way to the right. Accurate classifications are colorized yellow to green, with green indicating high confidence in the classification and yellow indicating low confidence. Hover over specific examples along the bar to see their identity and their corresponding confidence scores. Additional information is available by clicking on the comparison pairing listed below the classification bars. Here, each data point is ranked by classifier value or importance. This is a reflection of how well it predicts classification and how critical it is to making classification decisions. The entire suite of tools here behaves identically to those in the Select Best Data Points module, so I recommend watching that earlier video for a tutorial on how to use the various components here. In addition, you can access the numerical data for all of the data points assessed in machine learning under the Data Points View/Export button. This reveals a table of data that can be exported in different formats. The data includes retention time and M over Z coordinates for each data point, different chromatography or mass spec protocols used if multiple have been included in the analysis, the classifier value or importance score, which comparison the score is relevant to, and any information that comes from the dictionary file you provided earlier. Additional tools appear when dealing with larger data sets and multiple comparisons. Here is a workbook comparing multiple different breast cancer cell lines. Pairings were chosen in an earlier module, and different selections might yield different insights. For each pairing, visualization of the decision value ranking, retention time, M over Z, and abundance information can be presented as before. The new tools are parallel axes plots of classifier value scores for each data point across each pairing, as well as average abundance values for each data point across all outcome categories, in this case, the different cell lines. The decision value or importance plot shows whether a single data point, highlighted in green, might be relevant for classification in one pairing or multiple pairing. Meanwhile, the average abundance plot shows trends for abundances across all categories, helping reveal patterns of expression. These parallel axes plots are highly complex when dealing with large numbers of data points, but the plots are interactive. Draw a box around a region within the plots, and any trend lines that do not cross through the selected region are excluded, allowing selection of groups of data points with specific importance or expression patterns. In both the example workbooks I've shown you here, the classifier is highly accurate and all data points selected have high classifier value scores. But this is not always the case. Classification of examples in a completely unrelated study yields frequent misclassifications and lower confidence scores. Incorrect classifications appear to the right of the dark hash mark and are colorized yellow to red. Red indicates incorrect classification with high confidence, and yellow indicates incorrect classification with low confidence. The overall purpose of this tool is to leverage machine learning to refine our understanding of which data points are most critical and closely connected to biological differences in the examples. This allows identification of data that is most relevant to biological differences. It also allows easy visualization of which categories can be readily distinguished based on the data. Up next, I will demonstrate how to use the cluster analysis module to view the relationships between the data points identified by machine learning based on shared expression profiles.